everyone. Welcome to episode number 680 of this here electronic engineering podcast called Amelia's Weekly Fish Fry. Brought to you by eejournal.com and written, produced, and hosted by me, Amelia Dalton. Folks, the AI boom is here. And while everyone seems to be talking about bigger models with faster GPUs, there's a whole other side of the story happening behind the scenes. And that's the infrastructure making all of it possible. Because it turns out building real world AI systems is a whole lot more complicated than just stacking up more GPUs and hoping for the best. This week, we're diving into the hidden challenges of AI infrastructure with David Driggers, CEO of Cirrascale. David and I chat about the surprising failure points that traditional data center planning often misses when it comes to large-scale AI deployments. While old assumptions about power, cooling, and networking simply don't hold up anymore, and why the just add GPUs strategy can be a recipe for disaster without a true systems thinking approach. Also, this week, I check out a new fourth state of matter discovered by AI. So, without further ado, please welcome Dave to Fish Fry. Hi, David. Thank you so much for joining me.
Hi, thanks for having me.
Absolutely. Okay, so first, David, talk to me about common or surprising failure points that you're seeing in real world AI infrastructure that traditional data center planning often misses.
Well, the main thing is that we've really crossed the chasm to requiring liquid-cooled data centers. We had been bumbling and stumbling along for a long time, whereas HPC has been doing, liquid to the rack for a while, 30 kilowatt plus. It was still nichey compared to traditional enterprise data centers. Now, water really is a requirement. The densities that we're dealing with, 50, 70, 100, soon to be 400 kilowatts a rack requires water. And it's still surprising to me that people are building new data centers today that are focused on air cooling when we just can't do it.
So, David, talk to me specifically about Cirruscale and share any recent challenges that you've solved for large AI deployment.
Well, and that's the other thing that's happening very quickly. Historically, data centers have had plans, to be built, 3 years, 4 years, 5 years out. Those were all gobbled up. And now with the AI just explosion, the size of the data centers, not just the density of the rack, but the size of the data centers, it's not just doubling or quadrupling. The size of the data centers we're being required to build or have are up 10 times the size that we are using just 2 years ago. And it's not just the data center, it's the suite size. Because historically, data centers, there have been big campuses or big setups, that were 50 megawatts spread across 10 buildings. That's not the requirement today. The requirement today, we need 20 megawatt single suites. So just a single data hall, one customer, one use case is 10 times the size that it was 2 years ago. So our biggest challenge has been finding data center providers who have been nimble enough to change their architecture, change their setup kind of mid-flight. I mean, literally working on the plane while it's in construction, going, oh, we were building this out to 2 megawatt data halls. You want what? Well, last month I wanted 4 megawatt data halls. Now I want 8 megawatt data halls. It is almost a 6 month to 9 month change in the size of data hall, which is just absolutely unheard of historically.
So, AI workloads are really shaking up the usual assumptions and designs we've been relying on for data centers, right?
Yeah, and again, the guys who build and design data centers, they're about the most conservative bunch within IT. They're used to building things slow. Data centers are supposed to live for 30 years, and all bets are off now because, like I say, the size of the data centers, the density of the requirements, it's changing, from a pure hardware perspective, it's changing every 12 to 18 months. And data centers are designed to be built slowly and then to last a long time. Well, how can you do that when the rack density went from 50 kilowatts a rack 2 years ago to 100 kilowatts a rack this year. Next year, it's going to 400 kilowatts a rack. I mean, these are just insane jumps in density.
Absolutely. So, David, what do you think are the key trade-offs engineers must actually face today when balancing power efficiency, cooling complexity, and network interconnect speed in AI systems?
So the thing that's driving density is the what we call a back-end networking, how the GPUs talk to each other and how the servers that hold the GPUs talk to each other. All that communication needs to be as fast as possible. And as those speeds increase, we have to move to different technologies that can't be long distance. They're measured in inches rather than in feet or in meters. So that's what's really driving this is having these systems work together. And for training, AI training in particular, that really is the key driver here.
So, David, there is an approach that is called just add GPUs, but that kind of strategy will fail without broader systems thinking's approach, right?
Yeah, these are entire solutions, and they're only just like historic supercomputers. That's what we're building. We're building supercomputers to crunch these numbers, to come up with these models, and they're the largest supercomputers that have ever been built. They require the most power, the most cooling, the most connectivity. But just like a traditional supercomputer, where my business actually came from was building HPC, building supercomputers, you're only as fast as the slowest link. I mean, one person, a single person could be running what are thousands or tens of thousands of server with a single job. But if one node fails, that job fails. And it's only as fast as the weakest link. And so we're always sitting there trying to find the next weakest link so that we can fix it to get the best benefit out of this entire cluster.
So, David, when companies start setting up their own sovereign and on-prem AI systems, what new infrastructure headaches pop up compared to just using big cloud providers?
It's extremely rare that somebody can do this on their own because so many things are moving, because it is a total system, not just the power, but the cooling and the networking and the density, as well as the management of these new platforms. It's rare that a company can do this on their own. They're typically going to have to go to a hyperscaler or to a neo cloud or to somebody who can really hold their hand and understands the entire solution. Now, NVIDIA is kind of trying to bridge that gap and provide especially your AI training type platforms, is trying to provide a recipe so that kind of anybody can do it, except that still doesn't go out to the data center. And again, the same trouble that we're having finding data center space, enterprises, this is a project for them. Whereas for us, it's our business. I have people who spend every day looking for, analyzing, architecting data centers. And that's just to keep up with, our business. This is even more difficult for an enterprise to do because they're working on one project. By the time they figure it out, it's already been changed. The technology is different, the capacity requirements are different, that space has already been taken. Historically, there's been lots of data centers to pick from. Right now, you're lucky if you can find anything within the next 12 months or 18 months. And again, the technology is still moving forward. So just because you found the data center, by the time you deploy it, the technology may have changed and you may have to change that data center. So going to a neo cloud, going to a hyperscaler, going to somebody that you can make a just-in-time decision or not make a 30-year. Remember, if they're building their data center, it's a 30-year commitment.
Absolutely. All right, David, it's time for your off the cuff question. So, if you could have one meal right now, it doesn't matter if it's on the other side of the world, you need a passport to get there. What would you have?
Oh, probably go to Thailand and have their lemongrass soup.
That sounds lovely. Yes, please. Awesome. Well, this was super cool. Thank you so much for joining me, David.
Not a problem. Thank you for having me.
Have you heard of the amazing new research coming out of Emory University about dusty plasma? Okay, so a team of theoretical and experimental physicists at Emory University recently published a study in PNAS demonstrating that AI can do far more than just predict outcomes or process data. By integrating laboratory observations of dusty plasma With a specialized neural network, they proved that artificial intelligence can actually assist in the discovery of entirely new laws of physics. Justin Burton, an Emory professor of experimental physics and senior co author of this paper, explains their findings like this. We showed that we can use AI to discover new physics. Our AI method is not a black box. We understand how and why it works. The framework it provides is also universal. It could potentially be applied to other many body systems to open new routes to discovery. All right, let's back up a second and talk about dusty plasma and why it's so important. So, as most of us undoubtedly know, plasma is often called the fourth state of matter. In this state, gas becomes ionized, meaning electrons and ions move freely and create unique properties such as electrical conductivity. Plasma makes up about 99.9% of the visible universe, from the solar wind streaming from the sun to lightning strikes on Earth. But dusty plasma, well, that's found in additional charged dust particles and can be found in many different environments, from the rings of Saturn to the Earth's ionosphere. On the moon, weak gravity allows charged dust to hover over the surface. Think about when astronauts walk on the moon and their suits are covered in dust. On Earth, dusty plasma can form during wildfires when soot mixes with smoke. These charged particles can cause a slew of issues with radio signals, making communication a whole lot more difficult for firefighters. So, this team from Emory studied dusty plasma and similar materials by recreating them in controlled experiments. They suspended tiny plastic particles in plasma filled vacuum chambers to simulate more complex systems. And by adjusting the gas pressure, they were able to mimic real world conditions and observe how these particles respond to different forces. For this project, this team developed a tomographic imaging method that was able to capture the three-dimensional motion of these dusty plasma particles by using a high-speed camera that records images as a laser sheet moves through the chamber. These images were then combined to reconstruct the positions of dozens of particles over time, which allowed researchers to track their motion in detail. Now, training the AI model to work with this data took a while. It took this team over a year to build it, because unlike systems trained on massive data sheets, this project had very limited experimental data. And their final model was able to separate particle motion into three main influences: drag from velocity, environmental forces such as gravity, and forces between particles. After training on 3D particle trajectories, this AI model was able to successfully capture complex interactions, including asymmetrical forces between particles. The analogy this team from Emory uses to explain this behavior is two boats moving across a lake. Each boat creates waves that affect each other. Depending on their positions, these waves can either push or pull the boats differently. Ilya Neyman further explains this principle like this. In a dusty plasma, we described how a leading particle attracts the trailing particle, but the trailing particle always repels the leading one. This phenomenon was expected by some, but now we have a precise approximation for which didn't exist previously. The results of their system also challenge earlier theories. One long-standing idea suggests that a particle's electric charge increases in direction proportion to its size. These new findings, however, show that while larger particles do carry more charge, the relationship is more complex and depends on factors such as plasma density and temperature. Another assumption held that forces between particles decrease exponentially with distance in a way that does not depend on particle size. The AI model revealed that particle size does affect how quickly these forces weaken. And this team's work specifically focused on non-reciprocal forces, where one particle influences another differently than it is influenced in return. By leveraging this specialized AI model, the team managed to describe these non-reciprocal forces with an incredible 99% accuracy, which is a huge deal since these forces are traditionally a total nightmare to measure and model. Ilya, the Emory Professor of Theoretical Physics and co-senior author of this paper, explains the importance of this aspect of their study like this. We can describe these forces with an accuracy of more than 99%. And what's even more interesting is that we show that some common theoretical assumptions about these forces are not quite accurate. We're able to correct these inaccuracies because we can now see what's occurring in such exquisite detail. So, where is this amazing research headed from here? Well, this team was able to develop a physics-based neural network that can run on a standard desktop computer. And they believe it offers a flexible framework for studying many body systems across a variety of different fields. Ilya explains it like this. I'll be teaching students from all over the world how to use AI to infer the physics of collective motion, not within a dusty plasma, but within a living system. And Justin Burton sums up the study like this. It takes critical thinking to develop and use AI tools in ways that make real advances in science, technology, and the humanities. I think of it like the Star Trek motto, to boldly go where no one has before. Used properly, AI can open doors to whole new realms to explore. From dusty plasma to Star Trek. All right. So if you'd like more information about Cirrascale or this new study out of Emory University, I've included a couple links below the player on this week's Fish Fryin' page on eejournal.com and in the description for this week's YouTube episode as well. Hey, have you checked out EE Journal on social media yet? Well, you should. You can find us at facebook.com/EEJournal. If LinkedIn is more your thing, I dig it. You can follow us or me on LinkedIn, and we are also on Blue Sky Social and Mastodon as well. And we have a YouTube channel. Folks, it is chock full of all kinds of techie videos, including our very popular Chalk Talk webcast series, hosted by me. Thank you everyone for tuning in. If you know of any cool new technology or heck you just want to chat, shoot me a line at Amelia, that's AMELIA, at eejournal.com, or post a comment on our forums on EE Journal. For the week of May 1st, 2026, I'm Amelia Dalton, and you've been fried.